for having me. I'm delighted here to be here and celebrate Brown's 250-year anniversary. And I'm particularly delighted to be one of the speakers. As Roberto said in his nice introduction, I'm going to be talking about learning from errors. So, to illustrate why errors are important in economics, I'm going to start with two examples, one taken from the physical sciences and one taken from economics. For the example from the physical sciences, I'm picking one that is important to many Rhode Islanders, the prediction of tides. Now, this is something where the underlying mechanisms are well understood and the variables are observable. So it's not surprising that the quality of the prediction is going to be very good. Of course, most prediction problems in the physical sciences are more sophisticated than that, but nevertheless, the level, the ratio of signal to noise tends to be fairly large. In economics and other social sciences, we're often not as lucky. And here I'm giving a simplified example about the relationship between cognitive test scores and at an earlier age and income at a later age. And there is a clear trend in the data. And if you do a statistical analysis, you will see that the relationship is statistically significant. But there's a huge amount of scatter. And overall, cognitive test scores explain a fairly low fraction of the variability in adult outcomes. Now, again, these are one reason for the difference between the two examples that is in one case we understand well the mechanisms underlying it, we can observe the variables. In the other case, we don't know exactly all the variables that should affect income, and there are variables that we know should affect adult income, but we can't observe them. Again, these are two examples from opposite ends of the spectrum. So, in most prediction problems in the physical sciences and economics lie somewhere in between, but in economics, problems look more like the graph on the right than the graph on the left. So this just as an illustration that noise is important in economics, both because humans are hard to predict and not all alike. So if you put two human beings in exactly the same situation, they're still going to behave differently. So we need noise in our models to account for a number of overlapping reasons. There are model imperfections, and these imperfections show up as noise to the researcher. People are heterogeneous, and that heterogeneity can be modeled as noise. And there are, of course, data limitations. Sometimes we know which variables we want to include in the model, but we simply can't observe them in the data sets that we have available, and we'll call that latent variables. At other times, we're slightly more lucky, and we observe error-contaminated measurements of the variables of interest, and we'll call that measurement error. So it's not surprising that the statistical analysis of economic data, and in particular the study of noise, would have received a lot of attention in economics. To fix the ideas, let's start with a very simple example where we have a true variable x star that is unobserved. What we do observe is an error-contaminated measurement of x star, and that we'll call x. There's an additive measurement error that we'll call delta x. And since there are two unobservables, but only one equation, clearly we won't be able to recover the truth at the level of each individual observation. Now, fortunately, we don't usually need to know the truth at the level of each individual observation typically averages over some population or subpopulation are sufficient. And so to see that, let's say that we're interested in studying the effect of some intervention on the economic well-being of individuals, and the object of interest is some average effect of that intervention on a subpopulation. So you can think of averaging the observables over the subpopulation of interest, and that amounts to averaging the truth and averaging the errors. Then if the sample size is large enough, then we know from the well-known law of large numbers that the averages will go to the expectations and of the corresponding variables. And if the measurement error has zero mean, then the errors will disappear asymptotically, so in the large sample. Of course, this is very simplified, because most useful models or estimators, even the very simple least squares estimator, is actually nonlinear in the mismeasured variables. And this additive decomposition between signal and noise no longer works. Sometimes you may have a more fundamental problem than that, in the sense that you may have measurement errors that don't have zero expectation, which we'll call a setting of non-classical measurement errors. All right, so there have been a lot of different strategies developed to deal with measurement error. For instance, there's a very large literature, especially in statistics, that assumes that the distribution of the measurement error is known. In that case, correcting for measurement error is fairly easy via so-called deconvolution analysis. But on the other hand, it assumes a lot of knowledge on the part of the researcher. Another approach is to attempt to collect so-called validation data. Okay? A validation data set is an additional auxiliary sample that actually contains the perfectly measured variables of interest. Now, again, that makes correction for the measurement error very simple if you can collect validation data set, a valid validation data set. But typically, validation data sets, when they can be collected, are very expensive to collect. And so true validation data sets are fairly rare. Today, I'm going to focus on approaches that are less demanding in the type of information, additional information required. And so, for instance, there are approaches that rely on repeated measurements. Repeated measurements, these approaches require at least 2 error-contaminated measurements of the truth. And that could come from observing the same variable repeatedly over time, or by having 2 different types of measurements of the same variable of interest, or simply interviewing different people, like a husband and a wife, about the same quantity, let's say household expenditure or household income. Other approaches rely on so-called instruments or instrumental variables. Instruments are to some extent more general than repeated measurements, in the sense that they're not typically measured in the same units as the underlying variables of interest, and they can be nonlinear related to the truth. Okay? But generally, instruments explain variations in the truth, but are unrelated to the errors. Sometimes, unfortunately, people don't observe repeated measurements or instruments in their data sets. And then an approach would be to try to use higher order moments beyond means and covariances from the data. So in that case, you don't have additional data, you just use the existing data more completely, although typically under stronger assumptions. If you're not willing to make stronger assumptions, then sometimes the only possibility is to try to bound the parameters of interest. Before we proceed, let's just quickly rule out a technique that may be the first thing that pops into people's minds when looking at measurement errors. At first, it may seem that minimizing the sum of the orthogonal distance squares from the regression line could be a good idea. However, orthogonality has no meaning if x and the dependent variable y are in different units. And more fundamentally, this presumes that the ratio of the error variances along x and y would be magically related to the slope of the regression line. To see that, think about what you do if you have errors only along y. If you have errors only along y, then you minimize the vertical distances. If you had errors only along x, then you would minimize the horizontal distances. Now, if you were to minimize some diagonal distance to the regression line, then it would assume that you know the expected magnitude of the relative variances of the errors along x and y. And in particular, if you were to minimize the sum of the orthogonal distances, that would assume that the ratio of the variances of the errors is somehow related to the slope of the regression line, which doesn't make any sense because the regression line is all about the signal, while the errors are about the noise, and there's no reason that they should be related in exactly this form. So this idea is really something that you don't want to do. We're going to start by talking about classical measurement errors, so measurement errors that have zero expectation. And we're going to look at approaches that don't make distributional assumptions or where you can't, you don't have access to a validation data set. For polynomial specifications, Hausmann, Ichimura, Nui, and Powell were able to derive a very nice closed-form solution expressing the coefficients from the polynomial regression as a recursive function of the observable moments of the data. That approach worked for both instruments and repeated measurements. For more general specifications, Hausmann, Nui, and Powell used an approach in which they approximated the general specification via a sequence of polynomials. This approach only worked for repeated measurements. It turned out that for instruments, the recursive function in the approximation would have to start at an infinite power, which was not possible. Then B looked at another approach using repeated measurements using so-called Kotlarski's identity, which is what we're going to discuss next. Kotlarski's identity is a very old but very powerful result that uses the availability of two error-contaminated measurements of the truth x star. The truth and the measurement errors are mutually independent, and at least one of the measurements has zero expectation. It turned out that in that case, it was possible to find an expression for the distribution of the truth x star in terms of just observable moments involving x and z, and the two measurements. Now, this is much more sophisticated than standard deconvolution, because in standard deconvolution, you assume that you know the distribution of the measurement error. It's also more sophisticated than assuming that you have a large number of measurements, a very large number of measurements available at each value of x star, and then just averaging out over the errors to average out over the variables to average out over the errors, because in Kotlarski's identity, all you need is 2 error-contaminated measurements at each value of x star. And that works because implicitly, in the expectations, you're actually averaging over different values of x star. So only 2 measurements at each value of x star are needed. Li and Wong derived a multivariate extension of this result, and Li applied it to a regression setting. It turns out that you can actually generalize Kotlarski's result beyond a multivariate setting even by relaxing some of the assumptions. And so here, you still need one independence assumption between the measurement error of one of the measurements and the truth. For instance, the variance of the other measurement error could vary with the level of x star, so you can allow for heteroscedasticity in one of the measurement errors. And more importantly, you can also allow for the measurement errors on the 2 measurements no longer have to be fully independent. Another refinement here is that we're directly expressing an expectation of a nonlinear function of the truth x star, in a known nonlinear function of the truth x star in terms of the observable moments. That turns out to simplify the derivation of the asymptotic properties of an estimator, and it also illustrates that this approach is very generally applicable because moments are the building blocks of most estimators. And so with this, you can handle models which, when you express them in terms of the true unobserved x star, take the form of nonlinear regressions, because then your moments just come from the first order conditions of residual square minimization. Can directly handle estimators that are expressed in terms of moments, such as the generalized method of moments. You can deal with maximum likelihood estimators because the first order conditions can be expressed in terms of moments. And finally, you can allow for this function, nonlinear function of the truth, to be sample size dependent via bandwidth parameter and do kernel smoothing in a non-parametric setting. Sometimes you don't have repeated measurements available. Instead, you will have instruments. And the assumptions follow here Hausman, Ishimura, and Wei-Powell, who focused on polynomial specifications. And the assumptions were also used in Nui and Wang and Shao, who did not manage to prove general identification. So here the setup is that of a nonlinear or non-parametric regression, where we have one measurement of the truth x star available, but we do have access to instruments that explain variations in the truth, but that are unrelated to the errors, as you can see in the conditional mean assumptions. Now, arguably, these assumptions are fairly weak in the sense that you have only one independence assumption, in this case in the instrument equation. It turns out, after some work, you can again express the regression function of interest, g of x star, in terms of just observables. Now, the expression may be a bit reminiscent of Kotlarski, but it's important to realize here that the quantities involved are a bit more complicated, and in particular, there's some divergences in the potential divergences in the integrals that you have to take care of. When the regression function is parametrically specified, it turns out that you can derive equivalent moment conditions, and that again simplifies the derivation of the asymptotic or large sample properties of the estimator, because you can use standard techniques. This setting has been extended to quantile regressions, where you are interested in how the percentiles of the dependent variable change with the truth. And as a byproduct of that, you can also identify the joint distribution of the dependent variable y and the truth, which then implies that you can identify virtually any statistical quantity of interest. So far, we focused on classical measurement errors, so measurement errors that have zero expectation. Now, how can you think of moving away from classical measurement errors? One way of doing that is to think of an alternative centering restriction. So, for instance, you could think of replacing a zero mean assumption on the measurement error by a measurement error that has zero mode, zero median, zero quantile or percentile, and so on. So here it is assumed that the researcher knows from the start the centering correction that applies in his or her data set. It turns out that this alternative centering restriction is actually supported by the existing validation data evidence. So here I'm reproducing results from a non-parametric analysis by Bollinger that used a validation data set for self-reported income. Self-reported income is typically assumed to be measured with error. Here, in this case, the validation data set was taken from Social Security income, which was assumed to be true income. And then Bollinger found that the median of self-reported income, conditional on true income, fell along the diagonal x equal to x star. At the same time, he also found that the mean of self-reported income, conditional on true income, did not fall along the diagonal. And in particular, the lower income households tended to over-report income. For the same data set, Schennach and Tarozzi found that at each quartile of true income, self-reported income fell at the mode. Was at the mode of self-reported income was at the truth. And so this is a setting where, at least for self-reported income, a zero median and zero mode assumption on the measurement error would be justified, but the classical measurement error of zero mean assumption would be invalid. There may also be cases where an alternative centering restriction may be useful when you have other data problems. Here I'm graphing the distribution of the observable x condition on the truth. If you have truncation, well, truncation changes the mean, but it preserves the mode as long as the truncation isn't too severe. If you have censoring, again, censoring affects the mean, but it preserves the median as long as the censoring isn't too severe. You can also think of other types of measurement errors, for instance, a case of systematic underreporting, which might happen if you interview people about their texting habits while driving, which is something that bothers me a lot. So maybe in that case, you would be able to assume that the mode, the truth is at the 100th quantile. Now, to give a more specific example, let's assume that we have access to 3 error-contaminated measurements of the truth. At least 2 of these measurements could be distorted measurements of the truth, so they could be instruments or they could be dependent variable of a regression. Of course, all these measurements could just be repeated measurements in the sense that we've discussed before. And I call these observable measurements x, y, and z. Ideally, you'd be able to use the observed density of x, y, and z in order to identify the unobserved density of the truth, x star, and the distributions of the measurement errors. So let's assume that the observables x, y, and z are mutually independent, conditional on the truth. Now that does not mean that the observables have to be independent. It just means that any dependence amongst them would have to be explained by the truth and not by the error, say. In that case, it turns out that you can write the distribution of the observables in terms of the distribution of the unobservables via this integral equation. And then the question of identification amounts to asking whether there exists a unique solution to this integral equation. It turns out that with our centering restriction that the distribution of one of the measurements conditional on the truth is centered at the truth, the answer to that question is yes. The proof involves writing this integral equation as a composition of three linear operators, which after some work can be shown to be equivalent to a spectral decomposition of some operator, which under some assumptions, including this crucial centering restriction on the measurement error, can be shown to be unique. This result is also interesting because it generalizes the results on the widely used linear factor models to nonlinear and non-classical settings. And it also could be seen as generalizing the discrete factor models along the line of Putzkoll's work to continuous variables. So far, we've assumed that we have instruments or repeated measurements of some form available for identification purposes. What if that is not the case? Well, in this case, let's go back to the simplest possible setting, a linear regression model. It's just one measurement of the regressor x star. Fully classical setting. The regressor and the measurement and the disturbances are independent and have zero mean. It turns out that unfortunately, the most natural case where everything is normally distributed is actually not identified. Now, a normal here plays a special role because linear combinations of normals is normal. And normal distributions are entirely determined by the means and covariances. So you can't make use of higher order moments from these distributions for identification purposes. As soon as you move away from full normality, then there's a hope for identification. And that would come from exploiting the full independence assumptions and using, for instance, higher order moments or Q-mins for identification of the slope coefficient of interest. There's a very large literature on this. Again, that goes back to the early part of last century and is still being worked on these days. It's a very long history. But what if you go away from the linear setting to nonlinear, non-parametric regression settings, still under a completely classical setting with a full independence? Do things get better or worse? Turns out that things actually get better in the sense that the only function of form amongst functions that are sufficiently regular to be plausible that may not be identified is this 4-parameter family. And even that family is not identified only for very specific distributions of the truth and the errors. And by the way, setting d equal to 0 here gets us back to the linear setting from Bryer-Soll's result. Not surprisingly. Intuitively, nonlinearity helps because it destroys the normality of some of the variables. Now, if you're not willing to make strong assumptions, then perhaps one has to use a different strategy under weaker assumptions and derive bounds or attempt to derive bounds or inequalities on the parameters of interest. That amounts to setting of set identification as opposed to point identification, which we have focused on so far. And in set identification, you would try to find a set of possible solutions to weak constraints rather than a single solution to stronger constraints. This is a very active literature in econometrics. To motivate set identification, in measurement error models in particular, and more generally in latent variable models, proving point identification may be difficult or may require strong assumptions, as we've seen. On the other hand, an identified set that may be derived under weaker assumptions may still be sufficiently small to show that the hypothesis of interest is unlikely to be true. Ideally, you want researchers to impose only the restrictions that they're willing to make for their data set, and then the method will indicate what inference they can make from the data. But it should be said that analytic derivation of an identified set may be difficult or impossible in all but the simplest settings. Now, one of the simplest and oldest examples of set identification are the first bounds on the linear errors in variables model. So again, back to the linear model with one measurement of the regressor x star, fully independent errors and truth, classical setting. And it turns out that in this case, the regression of the dependent variable on the observable regressor always underestimates the slope coefficient of interest. And that is known as the iron law of econometrics, or the regression to the mean effect. Now here, the problem is completely symmetric in y and x. So it turns out that the upper bound on the slope coefficient is given by the reciprocal of the slope coefficient of the regression of the observable x on y. Now it turns out that these bounds are tight in the Gaussian case, which is the unidentified case, as we know from Bryer-Soll's result. So unless you're willing to make distribution assumptions that move you away from this Gaussian case, these bounds are really as good as can be. The setting has been generalized to multiple regressors by Klepper and Neumann. But again, it's a very simple bounding example. How can you think of bounding more general models with unobservables? For that, let's briefly review or introduce the so-called generalized method of moments, which is widely used in economics. In GMM, you set a vector of expectations equal to 0. The expectations are of a nonlinear known function g of the data x and a parameter vector of interest theta. This setting is simple enough that very general results can be derived, and at the same time general enough that it covers most estimators used in economics, such as regressions, maximum likelihood, most statistical tests, and so on. If you want to extend that setting to unobservables, then you can think of introducing an unobservable as a potential argument of the function, moment function G. So this can be done with many different latent variable models. So for the measurement error models, you could just think of U as being the true value x star, that is unobserved. When you have interval value data, which is where you assume only a data range in which the range in which a data point falls, but not the true position within that interval, then the unobservable could just be the true position within that interval. In factor models, U could be the factors. In a state space model, U could be hidden state. If you have unobserved heterogeneity, U could be an individual type. But in general, allowing for latent variables is a very difficult problem because in principle, you have to consider every possible distribution of the unobservables that is consistent with the model. So in particular, when you have a GMM framework, you'd have to consider every possible distribution of the unobservables that makes the moment condition satisfied. It turns out that you can actually focus on a much smaller class of distributions, namely all entropy maximizing distributions of the unobservables that make the moment condition satisfied. Entropy maximization has a long history as a device to model lack of information under some constraints. And it basically, intuitively, it spreads the amount of uncertainty as much as possible. Here, it's interesting that this is exact equivalence. And you can simplify things further, providing the entropy maximizing distribution as an exponential distribution indexed by a parameter vector gamma that has the dimension of G. So the question of considering all possible distributions of the unobservables that make the moment condition satisfied is simplified to finding a small dimensional parameter vector gamma that summarizes everything we need to know about the distribution of the unobservables. And amazingly, in the end, you get back to moment conditions involving only the observable variables and with a slightly augmented parameter vector that includes not only the parameter vector of interest theta, but also this nuisance parameter vector gamma. So here, let's just look at how this tilting via gamma works. In a simple example with just two moment conditions that impose a mean and a variance of an unobservable, completely trivial, use this example, but nevertheless. So here we have this exponential distribution indexed by gamma. And then as you change gamma along one direction, the probability increases along that direction until you reach a point mass. And then as you vary gamma in different directions, you can reach distributions that have a mean anywhere within the convex hull of the values of G, which is exactly the same range of means that you could reach by considering every possible distribution of the unobservables. And that's why tilting via this gamma works. And when you then integrate out over the unobservables via this exponential entropy maximizing distribution, you don't have to do that analytically. You can do it numerically. And for those of you familiar with that literature, you would just use this exponential entropy maximizing distribution in the framework of the method of simulated moments. So, and that's why I called this method entropic latent variable integration via simulations, or ELVIS. Much easier to remember. The method replaces the infinite dimensional distribution of the unknown, unobservables, by a lower dimensional unknown parameter vector gamma. method avoids trying to find the possible distributions that make the moment condition satisfied, and replaces it instead by computer-intensive but automatic simulation-based numerical method. And the purpose of this approach is really to bypass the need to establish point or set identification, which can be a very difficult analytical process. And you instead have an approach that works in both settings. And the moment conditions that you obtain involve only the observables and turn out to have some nice computational properties with respect to this nuisance parameter vector gamma. So let's just give a couple of examples from the errors and variables literature in particular. Here we're back to the linear errors and variables model, where we've known that under full normality we're not point identified, we're only set identified. Okay? And so here the little diamonds on the top are the bounds from the forward and reverse regression that are obtained analytically. And we know that when we're in a non-normal setting, then we're point identified. Okay, so this is a case that has already been worked out analytically. But when you look at the objective function from Alvis, you can see that it nicely distinguishes between the two cases, because in the set identified case, you have a fairly flat region in between the analytic bounds. So, of course, the true purpose of Alvis is to allow you to look at models for which analytically people have not been able to derive solutions. And so here's what I still consider a very simple model, a polynomial errors and variables model. We have only one measurement of the truth. We know that under full independence, and we know from Schennach and Hu, that this model is actually point identified. But if you're only willing to impose these weaker zero mean and uncorrelatedness assumptions, really nothing is known. We don't know anything about point identification. Nobody has been able to derive an identified set. So this is a setting where Alvis would be very useful. And here we're graphing the objective function from Alvis, which measures how well the moment conditions are satisfied for different values of the parameter vector. And on the base plane, I'm giving the confidence regions for different levels of significance. And there's this little dot in blue, and that's the truth, which of course in reality you would not observe. I'm not going into the details, but this Alvis approach is actually can be used with different existing methods for inference. Okay, so what is interesting here is that even though analytically nothing is known, the computer code is virtually identical to the linear model that we saw before. In some sense, it's easier because we have a few moment conditions versus 27 moment conditions for the linear case. Right, so to start concluding, one thing that I like about having worked in the measurement error literature is that the techniques used actually go well beyond measurement error models. And so, for instance, people have used measurement error techniques for identification purposes in auction models, where you could think of using bids on a good as repeated measurements of an underlying common value. And here people have used both Kotlarski type identities and Hu and Schennach type identities. Measurement error techniques can also be used to help in the identification of nonlinear panel data, which is data indexed by time and individuals. And in this case, you could think of using outcomes over time as repeated measurements of an average outcome. And again, people have used Kotlarski type identities and Hu and Schennach type identities. Then, of course, factor and state space models are closely related to measurement error models in the sense that you can have generalized repeated measurements where observable indicators may measure more than one of the unobservable factors. And here I'd just like to spend a minute because I've worked in this area with co-authors Kunha and Heckman, in which we derived a nonlinear dynamic model of skill formation with interacting cognitive, non-cognitive skills, and investments into skills. And the variables of interest were ultimately adult outcome measures such as schooling or crime. And the model was a dynamic factor model that allowed for a large number of noisy measures of the latent skills and investments. And of course, this is a setting where you'd assume that measurement error would be particularly important because these things are very difficult to measure. And we looked at non-separable and potentially non-classical error structures. In terms of findings from the preferred model estimates, they suggested that cognitive skills are most malleable early in life, while malleability for non-cognitive skills remains similar through childhood and adolescence. So that remediation strategies in adolescence for disadvantaged children should really focus on fostering non-cognitive skills, while investments in the early years would be important for the formation of cognitive skills as an adult. And then some policy simulations from the model suggest that there's thankfully no trade-off between equity and efficiency, in the sense that optimal investment strategy to maximize aggregate schooling attainment or to minimize aggregate crime would be to target the most disadvantaged at younger ages. Now, we're not claiming that this is the answer to these very important economic questions, but we do hope that taking seriously the econometrics involved would stimulate further research into this area. So, concluding slide. I haven't gone back all the way to 250 years, but the measurement error literature that we have seen goes back into the early parts of the last century. We had fundamental results on linear models, typically under pretty strong independence assumptions. In the last 25 years or so, a lot of progress has been made towards identifying nonlinear models. And recently, really, people have focused on nonlinear models from all angles, trying to use more readily available information under weaker assumptions. So for instance, replacing independence assumptions by conditional mean assumptions, or even moving away from the classical measurement error assumptions and trying to allow for some types of non-classical measurement errors. It's always difficult to predict where the future will go, and I don't dare to even think 100 years ahead. But one possibility is, of course, that we'll have methods that exploit availability of large data sets and computing power, because our brains don't improve as much as computing power does. So it may be easier to do things numerically and purely analytically. You can also think of having hybrid methods for identification purposes. And of course, there's a very large literature on survey design. Okay? And so now that we have new results in terms of identification of these latent variable or measurement error models, you could think of designing surveys that don't try to extract the truth at the level of each individual, but instead try to extract variables that we know can be used to identify what we're interested in. And this is the end. So.
Thank you.